Okay, now what we're going to do, we're going to implement a one-dimensional convolution neural network to classify our sentiment data, IMDb sentiment data. So to do that, what I'm going to do, I'm going to copy this existing notebook so that we can maintain it parallelly, and I'm going to give a good name to it with Alright. So in the first step, majority of the steps would be very similar to whatever we have here. So we have to include few additional dependencies. So to do that, let me move all the existing layers to a single import, and the new things we are going to import here. First of all, what we have to import is the convolution 1D. Alright, so next we need to import global max pool. Global max pooling 1D. We need to import another dropout layer. It's a special kind of dropout, that is spatial dropout, and that is again going to be one dimensional. And I hope we are in good shape to start our model. Alright, import is done. Now we are going to change the output directly to convolution. Number of epochs we can increase little bit. Let it be 5 for now. Batch size is almost same. Dimension I'm not going to change it. Only skip word is supposed to be the same as well. Next thing what I'm going to do, I'm going to increase the max review length. So I think our model can handle much higher size than these whatever we have. Let's make it 500. Okay, padding and truncate should be same. We need to add one more dropout here, that is embedding dropout. Okay, so I'm going to drop 2% of them. We have one dense layer, let it go down for a while. We need to import the hyperparameters for our convolution layer. In comp we have only one convolution layer, so we don't need to worry too much about the numbers. I'm giving the name one conv, so we will have around 256 different kind of filters, and the kernel size for conv layer is 3. You can play with this value, you can give some higher values as well, and we are going to use a max pool as well, so we can increase the dense layer size is around 120, or if little bit of higher than this, and dense dropout 2.5 should be fine, 0.5 should be fine, or we can decrease it a little bit. Let's make it 0.25. I hope we have all the hyperparameters needed. So alright, so it's done. Now the data load point of view, we are going to have the same way to load the data. It is working. Okay, data load is done. So size is same, we don't need to review these details, and this content, it's good to have, but I'm not going to show you these examples. Next, what we are going to do, we are going to do the pre-processing, and it is same. Now I'm straight going to the design section. So here we are going to do lots of modifications to include our new kind of layers. So first it is going to create that embedding layer, output direction, max movie length. Okay, all three of them are different. So we need to include the dropout layer here. Model dot add spatial dropout, and we need to specify the dropout probability or percentage. Alright, so we're done with the dropout. Now we need to include the convolution, 1D convolutions, and the layer is designed in such a way that it can work on the embedding layer, on top of embedding layer itself. So we don't need to make it one-dimensional flattened layer. So this flattened layer may not require. So let me construct one by one. So let me include the convolution layer, convolution 1D. Okay, so we need to specify a few of the parameters, that is number of number of convolutions, filters, then kernel size, and we need to specify the activation function as well. So convolution is done. We are going to add global max pooling layer. Earlier you must be familiar with the max pooling layer. This is special kind of max pooling layer that is that works great with the natural language processing, and so normally it considers the whole kernel size and whole filter size while pooling that content. So rather than using any passage, so we don't need to specify any parameters while calling this global max pooling. Next step, as I already told, that we don't need this flattened layer anymore. We are using this one-dimensional max pooling. So next point we are going to do is dense layer. Dense layer is supposed to be the same size, and dropout dense and activations. Alright, so model architecture point of view, we are pretty much done with this. So let's see, it's created while. So we can see one thing, like the number of parameters got reduced drastically, almost 50%, like whatever we had earlier. It's the 700,000, now we have 400,000. It's good for us, but training process may take a bit longer time than whatever we used to take earlier. And compile point of view, we are going to keep all the parameters same. We're going to use, we need to create a new directory for our output files, because it's a different model, and I'm not also changing these checkpoint details. Next thing we're going to do is let's start our training process. Okay, nothing should change in this particular line also. Only major difference was the model architecture. Now we are calling a convolution layer. In the previous in the previous dense layer itself. Now this network can be called as CNN or convolution neural network, and we are using CNN for natural language processing to understand to the kind of sentiment users had while writing the movie review or kind of feedback they had for the movies. So these model may take a bit longer time to be trained on, and let's wait for it. And all right, so our model training is done. It took a bit longer time and approximately 400 seconds, 450 seconds for each iterations. And I'm running it in a CPU mode. That's why it is taking this much long time. And if you are running it in a GPU mode, I'm sure that you can get this epoch completed within 10 to 15 seconds. What we have seen here in the second epoch itself, we got the highest validation accuracy, that is 86.52%, and third, fourth and fifth, those are also very close. But what we are going to do, we are going to use the second iteration itself for our predictions. So what I'm going to do, I'm going to load the weights for the second iterations. 1, 2, 3. Okay. This is 0 index, so it should be epoch number 0, 1. Okay. So I'm loading the model, loading the weights. In fact, weights are loaded. Now I'm going to do the predictions. It also may take a bit longer time. Let's wait for the prediction to be done. It is expecting around 1 minute to complete. And we're done with the predictions. So next what I'm going to do, I'm going to plot the model outcome, these same plot whatever we did for the dense network. What we see here, the predictions are much more polarized, like in the 0 and 1, they are predicting more confidently that and there is a big spike in the positive sentiment here. Earlier it was around 4,000, and now we can see it has reached around 8,000. On the other hand, the negative sentiment, or it's also increased a little bit from 0 to from 6,000 to 8,000. All right, so I'm sure the model has started predicting in a much better way with the use of this convolution layer. So let's see what is our AUC score now, whether we are able to beat this 92.73% benchmark, while our validation accuracy is much higher than whatever we had in the previous dense network layer. That was 83%, I believe, 84.5%, 84.6%. Now we have 87.5%. All right, so it's time for the moment. Okay, we got validations AUC around 95% here, and so that is pretty decent. And with this simpler version of the model, we can play with these hyperparameters a little bit, like increasing the number of neurons in the dense network, or number of neurons in the convolution, number of filters in the convolution layer, or increasing the kernel size, dropout size, and all these sort of things, or removing the stop words or most frequent words. So all these sort of things you can try. And definitely if we start tuning the hyperparameters, and the model performance will improve a little bit, and you can expect it will reach around 96.5 somewhere. I think that is the previous best figure I got with the very bare minimum number of hyperparameter tunings operations. What is next? Next we are going to have another set of theoretical sessions to take one step ahead and to understand another important kind of neural network, that is recurrent neural network. And we are going to discuss the theory section first. And once you have clear understanding about what those neurons and neural network looks like and how do they work, we are going to come back to this same notebook, and we are going to implement all those kind of recurrent neural network to predict these sentiment classification problems. Okay, let's go. Let's have a deep dive into recurrent neural network.